Hi there, and welcome to today's class. For today's class, I'll be revising the JAMB past questions and answers on work, energy, and power. But the first question here says the dimension of power is dash. Let's get dimension for power. So power dimension. For us to get dimension, first of all, we have to get the what's it called? We have to get the mathematical expression for power, and mathematically, power is simply equal to work done all over time. All right, if this is true, for work done, let's break work done down. Work done is simply force times distance. Let's call distance S all over time. Let's call this T. Again, breaking this further, for force, the dimension for force, we know that force is equal to mass times acceleration. For mass, the dimension is capital M times acceleration. For acceleration, the dimension is L t to the power minus 2. So mass times acceleration times distance is L all over time is capital T. So this is how we do dimensioning, all right? I've taught the whole concept of dimension in our previous class, okay? I'll leave a link to the video on dimension in the description of this video, right? So you see, or you can just go check for the video on dimension and you see how we got all of this. All right, let's proceed. This is equal to, if I work on this, this is equal to, take the M, I'm having capital M here, take the L's, from here I'm having L times L, that gives me L squared, dot, take the T's. This one here is T to the power minus 2. Don't forget we have a denominator here. This denominator becomes all over T, which can be written as 1 over T. So it's the same thing, right? So if I shift out numerator, I'm having M, L times L is L squared, T to the power minus 2. I'm left with 1 over T. Write this one here down in, write it down in index form. I'm having M L squared T to the minus 2 times this one here in index form gives you T to the power minus 1. If I multiply this, I'm having L squared T into, if I multiply same days, I'll simply add the power. So it becomes minus 2 times, okay, T times T. I'm adding the power. So it becomes minus 2 plus minus 1. Plus minus is minus. So minus 2 minus 1 gives you minus 3. My correct option here is L squared T to the power minus 3. And that is option A. That's my answer. All right, let's look at the next question there. The next question here says the maximum kinetic energy of a simple pendulum below occurs when the board is at what position? All right, that's the question. So quickly, I'm going to sketch this. So you have 5 positions here. You have this one here, 1. You have this one here, 2. You have this one here, 3. You have this one here. Then finally, you have this one here, this. All right, so my positions here are 1, 2, 3, 4, 5. So they're asking the maximum kinetic energy occurs at what point? What point of the maximum kinetic energy occurs? So here's what to note. We know that kinetic energy, Ke, as we know, is equal to half times mass times velocity squared. This is the formula for kinetic energy, half mass times velocity squared. Now, since mass is a constant, it means kinetic energy will be properly dependent on the velocity of a body. Now, if that's true, the question is here, in which point here do I have my maximum velocity? Now, here's what we know. For this here, if I have a pendulum bob and I swing it, you observe that the pendulum bob goes this way and swings back this way, swings this way and swings back this way. Now, what can we infer from that movement? Now, when an object stops moving, it means that its velocity is 0. So note that. So in a case where I swing the bob goes this way, stops moving here and comes back, stops moving here and comes back, it means that my velocity is 0 at 2 points, which is 0.5 and 0.1. So at 5 and at 1, so at 5, at position 1 and 5, I have the minimum velocity, which is 0. So it means that if that means for this question here, if you're being asked to find the point where your kinetic energy is minimum, the answer will be at position 1 and position 5. The reason being that at these 2 points, velocity is what there? 0. So it becomes 0, it stops moving, and then it goes back and swings. Goes to 1, it stops moving, becomes 0, and comes back to this. So these are the 2 minimum points, so they cannot be the answer. So I'm left with these three options now, 2, 3, and 4. So which of them will be the answer here? Of course, for this case here, the maximum, the greatest force will be found at the center here, 3. So this is where anchors everything. So at this point, it becomes the greatest force, and then moves like this. You have some velocity here, but if you do the experiment, the greatest velocity is found at this point here. So the answer will be 3. 3 being the fact that the maximum velocity occurs here. So V max, the maximum velocity of a simple pendulum swing occurs at this point. So if I have V max at position 3, my maximum kinetic energy will also be at position 3. So the answer there is C, 3. That's your answer. All right, next up, please. Next up says a man of mass 50 kg ascends a flight of, that should be stairs, 5 meters high in 5 seconds. If acceleration due to gravity is 10 meters per second squared, the power expended is dash. Well, let's get this done. So here, solution, we are being asked for power. Let's list out given parameters. In JAMB, you don't have to list out. Just go shoot and solve because you don't have the time. But for this one, I'm just trying to list out the parameters so you can understand the solving better. So what am I giving here? Number 1, I'm giving mass. Mass as equal to 50 kilogram. Number 2, I'm giving height. Says stairs of height. I'm giving height as equal to 5 meters. Number 3, I'm giving time t as equal to 5 seconds. All right, you have to find the power. They give you g. They say you should take g as 10 meter per second squared. Okay. So recall that power is equal to work done all over time. And we said work done, the formula for work done is mass times gravity times height. This is the formula for work done in a force field. Mass times gravity times height all over time. If I put in values, mass is 50 times gravity. Gravity, they said you should use 10 times height. Height here is 5 all over time. The time given here is 5 seconds. So I have 5. So find power. So from here we can see that 5 will cancel 5 becomes 50 times 10. That gives you 500 watts. So going back to the option here, the correct answer here is option D. Let's take yet another set of questions. All right, the next question here says, an object of mass 20 kilogram is released from a height of 10 meters above the ground level. The kinetic energy of the body of the object just before it hits the ground is dash. Take g as 10 meter per second squared. All right, solution for this. Now note that for questions of this form, when you're asked to find the kinetic energy just before it hits the ground, the approach you give to this is the fact that you use the concept of the conservation of energy. And when it comes to conservation of energy, we say that kinetic energy is equal to potential energy. That's the formula for this. So I'm saying that in this case, you say that kinetic energy is equal to potential energy. This is the approach you give to this question when you're asked to find kinetic energy just before it hits the ground. This is the approach you give to this. And don't forget that potential energy is equal to mass times gravity times height. So that means that my answer is equal to the mass here. It's 20 kilograms. So 20 times gravity. So you should use 10. Okay. times height of 10. Okay, so if you multiply this is 200 times this is 2000. My answer is 2000 joules. So the kinetic energy is equal to 2000 joules, and that is option B, 2000 joules. Moving on, next question here says an object is moving with a velocity of 5 meters per second. At what height must a similar body be situated to have a potential energy equal in value with the kinetic energy of the moving body? Quite an interesting question. So let's look at this. First things first, it said an object of mass. Okay, it said an object moving with a velocity. So I'm given velocity v as equal to 5 meters per second. Okay, they said at a height. Okay, say at what height must a similar body? Now, when they say a similar body, what does it mean? It means that the two bodies have what there the same mass. That's a key concept. So when you're told similar body, it means they have the same mass. Okay, so at what height must a similar body be situated to have a potential energy equal to the kinetic energy of the moving body? So how do we solve this? So we are saying that at what height should the kinetic energy be equal to potential energy? Now, kinetic energy, as we know, is half times mv squared. That's the formula for kinetic energy. Is equal to, for potential energy, my formula is mass times gravity times height. At what height should the potential energy be equal to kinetic energy? So I have this formula here. Now, one concept about mathematics is that if I have the same term on both sides of the equation, they can cancel out. So I'm saying m can cancel m here. It's correct. The value of v is given as 5. So I'll have that half into v squared is equal to gh. Put the value of v, I have half into v is 5 all squared is equal to g. We're looking value for g here. Nope, they didn't give us value for g. So should we use 9.8 or 10? So let me follow their previous example. For here, we use g as 10. So let me just assume g to be 10 here. So 10 into h. Okay. So work on this. What do you have there? That becomes half into 5 squared is 25. So half 25 is equal to 10h. All right. So half of 25 is 12.5. Okay. So half of 25 should be 12.5 is equal to 10h. To get h, I'll divide both sides by 10. To divide this by 10, divide this by 10, I'll have that h is equal to, divide this, I have 1.25 in meters. Let's see if we have the option there. So we have 1.3 there, which is c. So we can approximate this to be 1.3 meters. So my answer there is option C, 1.3 meters. Okay, let's take yet another question. All right, the next question here says, if a pump is capable of lifting 500 kilograms of water through a vertical height of 60 meters in 15 minutes, the power of the pump is dash. Solution here. So first things first, they give us mass. The mass there as 500 kilograms of water. They said through a vertical height. Number 2, they give us height as equal to 60 meters. They said in 15 minutes. Time is equal to 15 minutes. We'd have to convert the time from minutes to second. And we said this is equal to convert to seconds. I'll have to multiply this. Becomes 15 times 60. So if I multiply 15 by 60, I have 900 seconds. So hence, my time in seconds is simply 900 seconds. So if you have to find power here, what do we have? Okay, so what do you have here to find power? For power, record that power is equal to work done all over time, such that the work done, we said, is equal to the product of mass times gravity times height. That's work done all over time. So bring in values. Mass is 500 times gravity. Gravity is a constant. Just as I used 10 here, let me still use 10. So 10 meter per second squared times height. The height given here is 60. This all over the time is 900 seconds. All right, let me punch this. So I'm having 500 times 10 times 60 all over 900. My value here is 333.33. Per is measured in watts. So I'm having 333.33 watts. If I look at this, the option here would be between C and D. What do you have there? So you have 3.3 times per 2, 1, 2. Your answer there should be D. D is given in 3.3 times 10 to the power 2 joules per second. Right. So another unit for power is joules per second. Is joules per second because work is measured in joules all over time in seconds. So joules per second. That's how they got joules per second. And it should be this. It should be the same thing because if I do 3.3 times 10 to the power 2 means I'm moving 2 times, which is 1, 2. So that's about 330 point this, which is the same thing as D. So they are the same thing. So my option is option D. All right, let's move on to the next one there. All right, let's look at the next question here. Our next question here says, a carpenter on top of a roof 20.0 meter high dropped a hammer of mass 1.5 kilogram and it fell freely to the ground. Okay? The kinetic energy of the hammer just before hitting the ground is dash. Okay, I think I've solved something like this similar. All right, so I'm giving this one here as an assignment. All right, so solve this question and leave your answer in the comment section. So I'll be watching. Okay, I've solved a question like this before now. All right, so I'm leaving this question here. Solve this question and leave your answer in the comment section. I'll check it out. So let's now do the next question, which is our final question. Final question here says, a bob of weight 0.1 Newton hangs from a massless string of length 50 cm. A variable horizontal force which increases from 0 is applied to pull the bob until the string makes an angle of 60 degrees with the vertical. The work done is question mark. All right, let's see how we can solve this question. All right, so let me get this question solved. A bob of weight 0.1 Newton. So first things first, solution. We are given the weight, or which is the force there, as 0.1 Newton. So I'm giving force as equal to 0.1 Newton. So we know this is force because the SI unit is Newton there. They said hangs from a massless string. So let me give you a diagram to explain this better. So I have this one here. I have this one is hanging here. Okay, they said the mass there is about 1.5 kilogram. Okay, now they said a horizontal force pushes this. So let's say we have a horizontal force coming here pushing this bob such that this bob now moves in this direction like this. So I will now have the bob going in a direction like this. Okay, something of this nature. So it moves like this. All right, so this is like a diagram. Let's call this the first case A. This was before the horizontal force was applied. Now when I apply the force, it goes like this to this point B. Okay, they said the mass of the bob, M is equal to 1.5 kilogram. They said we should also do what again there? Okay, they said the length of the string. So from here to here, the length of the string, from here to here, length about 50 cm. So this is 50 cm. That becomes length of this string. From here to here, it's about 50 cm. Okay, what next? Next in here, and that's basically because they say the angle is 60 degrees. So this angle here covered is about 60 degrees. Okay, what's next in here? What's the work done? So they said 60 degrees with the vertical. So 60 degrees between this one and the vertical line. This is my vertical line, there's 60 degrees. Okay. You have to find the work done. So work done, W, as we know, is equal to force times distance. Let's call distance S. The force, as we have here, is about 0.1 Newton. So that's not a problem. The problem will now be finding distance. What's the distance covered? Distance covered is from here up to this point here. That's distance, right? From this point here up to this point is called distance. What we have here is called an arc, all right? What's an arc? An arc is simply any path of the circumference of a circle. That's an arc. So what to notice this, that the distance S is equal to the length of the arc covered. So length of arc. All right. From the concept of circular geometry, we have that the length of arc, the formula for length of arc is simply equal to theta all over 360 times 2 pi r. All right. So this is the formula for the length of an arc. Theta over 360 times 2 pi r. So the theta here refers to this angle here, which is 60 degrees. You can say theta is equal to 60 degrees. Okay. R, what's the radius? Now, here's one thing to note here. For an arc here, the radius here will be equal to the length of the thread. Okay, so I'm saying this. Let's say I have this point here. Look at this. Let's say I have this point here, and I have a thread here, and I have this bob here. If I spin this bob around, it will go in a circular path. All right, so let's say I have a center point somewhere here, and I attach a string here to a bob somewhere here like this, such that the length of the string is from here to here. If I push this to move 360 degrees or in a circular path, it will go something like this. Let me try to sketch this. All right, so it will go this way, such that you observe that if I have a circle, please, this is just a board sketch, trying to illustrate something, to go like this. All right, so what do you observe? Observe that from here to here, like this, represented the length of the string from here to here. Okay, now observe that also from here to here can be called the radius of the circle. The radius of the circle is the distance from the center of the circle to any path of the circumference of the circle. Now observe that the distance from here to here, that's the length of the thread, will give you what there? Your radius. This is just a board sketch, right? If you do a proper circle, you observe that this distance from here to here, which is the length of the thread, will be the same thing as what there? The radius of the circle. So I'm saying in this case here, note that length of thread L is equal to radius of the circle. So I'm saying that radius is equal to what there? L. All right, so from here, this is equal to L is length is 50 cm, so 50 cm convert to meters means that L is equal to 50. To convert to meters, I'll divide by 100, and that gives you 0.5 meters. Okay, so if this is correct, let's now get the length of the arc. It means the length of the arc S is equal to theta 60 all over 360 times 2 pi into r. What's r there? This one here, 0.5. Okay, so I'll punch this correctly and see my value. All right, so punching this, what do I have there? So 60 all over 360 times 2 times pi times 0.5. That's about in like, let me use 3dp, 0.524 meters. Don't forget we're looking for the length of arc. Length is in meters. I'm having approximately 0.524 meters. So if that's true, it means that therefore the work done is equal to force, which is 0.1, okay, times distance, which is length of arc, 0.524. Multiply this, I'm having 0.1 times 0.524. That's about 0.0524. Work done is in joules, so I have joules. Or Newton, what again there? Newton meter. All right, let me check my options here. So I look at the options here. I have an option as 0.050. Okay. So the only option that is closer to this is 0.05. I have an option such as 0.050 joules, which is option D, which is the closest to this. So the correct answer here is option D. That's the correct answer, right? All right, so the small changes could be because of maybe I took, what was it? Maybe due to approximation here. That's why. So if you approximate here to 0.5, perhaps you get this answer here. Yeah. So may I use 3 dp, 1 to 3. Perhaps in their own calculation, they just use 1 dp, 0.5. So if you use it at 0.5, you have this answer. So that's just the difference. If not, it's still correct. So the answer here is option D. All right, so this is as much JAMB past question as we can take on work, energy, and power. So if you enjoyed this video, simply like this video, okay? So like this video right now, and then leave a comment. Tell us the other topic you'd want to see on this channel, and I'll make them available. Also, I've prepared over 100 courses on physics, chemistry, and mathematics, all right? Both for JAMB and WAEC students. So if you're interested in getting this course, simply visit my website, www.junaimmanuel.com/courses, and you see the JAMB/WAEC classes, all right? So get the course. It gives you a lifetime access to these courses. All right. Thank you very much, and see you in the next class.